this lecture, we will continue our discussion on second rank property tensors, but we will look at, we have already seen how these tensors transform due to symmetry operations for different crystal structure systems. Now, for a given crystal, I have a certain property tensor, and I want to find out what is a property in a certain direction in a crystal. For example, let us say in the direction of 111 in maybe monoclinic crystal, then how do I try to find out what should be the property in that direction based on the tensor for that crystal that I have. So, let us see, we will say property in a given direction and let us take a specific example of conductivity. As you already know that conductivity is a second rank tensor. So, I have applied, let us say, a electric field in a certain direction because of anisotropy. So, my electric field becomes, this is a vector, you can say this is the cause vector, and the effect vector, which is the flux, the current flow given by the flux vector, is in a different direction, and this is true for anisotropic crystals. Only in the case of isotropic crystals, we will have the electric field and the flux vectors in the same direction. So, how do I say I have a crystal and I put some, I make some electrical connection, let us say, to two opposite faces of this crystal, and I apply a electric field. So, I apply some potential to produce electric field in the given direction, and I can measure the flux in that direction. So, what now, looking from this thing, that in an anisotropic crystal, the flux J could be non-parallel to the electric field. So, I must take its components or component along the electric field, and let us say that component is J parallel. Then I can define conductivity in the given direction, that is along E, as sigma conductivity equals the flux component in the electric field direction divided by the magnitude of the electric field. And in fact, this is what exactly we are measuring when I do an experiment. Now, this J parallel, so let me define a unit vector n along the direction of the electric field, then the flux, the parallel component of the flux is simply the dot product of flux vector J with the unit vector n. Now, the unit vector I can determine by taking the electric field vector divided by its magnitude. So, this gives me the unit vector, and hence the parallel component of the flux vector is J dotting it with the electric field vector divided by the magnitude of the electric field. Now, in tensor notation, I can write the parallel flux as J I multiplied by EI divided by the magnitude. So, Ji is the component of flux along the xi direction. The electric field EI is the component along the xi direction. Otherwise, so if I expand this, this simply becomes J1 E1 plus J2 E2 plus J3 E3 divided by the magnitude of the electric field. Now, we already know that the flux Ji, the flux Ji equals the component of the conductivity tensor sigma ij multiplied by Ej. So, where j are the dummy indices, so it becomes a summation over j equals 1 to 3, and hence the conductivity in the direction of the unit vector n can be written as, by substituting Ji into this equation, I get the conductivity as sigma ij Ei Ej divided by E square. In fact, out here, so now I have, and now let me write this as sigma ij Ei upon E Eij upon E, not Eij, it is simply Ej, and thus the conductivity becomes sigma ij, and Ei upon E is a unit vector, Ej upon E is a unit vector. So, it is Ni and j. So, Ni and Nj are the components of the unit vector n. So, Ni and j are the components of unit vector n. Now, let us expand the above equation. So, the conductivity becomes, I am doing a summation over I equals 1 to 3 and j equals 1 to 3 on this equation. So, this will become sigma 1 1 n 1 square plus sigma 1 2 n 1 n 2 plus sigma 1 3 n 1 n 3 plus sigma 2 1 n 2 n 1, I can write it as n 1 n 2 plus sigma 2 2 n 2 square plus sigma 2 3 n 2 n 3 plus sigma 3 1, I will write it as n 1 n 3 plus sigma 3 2 n 2 n 3 plus sigma 3 3 n 3 square. Now, consider orthorhombic crystal. Recalling from the last lecture, what was the tensor for the orthorhombic crystal? It is simply only the diagonal terms survive, all the off diagonal terms are 0. So, the tensor is sigma 1 1 0 0 0 sigma 2 2 0 0 0 sigma 3 3. So, now if I look at this tensor very clearly in this equation, all the off diagonal all the terms containing off diagonal conductivities will go to 0. So, sigma 1 2, wherever sigma 1 2 is there, sigma 2 1 is there, everything, all of these will go to 0. So, this will go to 0, this will be 0, this will be 0, this will also be 0, this is 0, this is 0. So, only the diagonal terms remain. So, therefore, I can write the conductivity in the unit vector direction n. So, conductivity sigma in the direction of the unit vector n equals sigma 1 1 n 1 square sigma 2 2 n 2 square plus sigma 3 3 n 3 square. So, this is for the orthorhombic crystal. Now, let us consider the case of a tetragonal crystal. In the case of a tetragonal crystal, the tensor is sigma 1 1 0 0 0 sigma 1 1 0 0 0 sigma 3 3. Here again off diagonal terms remain 0, but the difference from the orthorhombic crystal is that two of the diagonal terms are now become equal. So, I have written the first and the second diagonal terms as sigma 1 1, and hence conductivity in the unit vector direction is sigma 1 1 n 1 square plus n 2 square plus sigma 3 3 n 3 square. Now, remember n 1, n 2, n 3 are the components of the unit vector n, and hence in fact the magnitude of n 1, n 2, n 3 are simply the direction cosines of the unit vector n. And since then these are direction cosines, therefore, n 1 square plus n 2 square plus n 3 square equals 1. That is a property of the direction cosines. And hence, I can write the conductivity in the given direction as sigma 1 1 into 1 minus n 3 square plus sigma 3 3 n 3 square. So, instead of I am replacing n 1 square plus n 2 square by 1 minus n 3 square. So, essentially if I look at I put this in the reference with x1, x2, x3 axis. This is x1, x2, x3, and let us say this is the unit vector direction along which I want to know what the conductivity is. Let this unit vector make an angle of theta with the x3 axis. So, then n 3 square is nothing but cos square theta, and thus I can write sigma in the direction of n as sigma 1 1 sine square theta plus sigma 3 3 cos square theta. Now, let us consider, we are still considering tetragonal crystal. Consider a direction in the x1 y1 plane. Again, just to remind, we are still considering tetragonal crystal system, and I have this conductivity given by sigma 1 1 sine square theta plus sigma 3 3 cos square theta. This is essentially, when I say x1 y1 plane, this becomes the plane perpendicular to the fourfold axis, or I could also call it as the basal plane. So, if I want to know what is the conductivity in the basal plane, so in the basal plane it means that the unit vector now is perpendicular to the fourfold axis, because the x1 y1 plane is perpendicular to x3, and x3 is where the fourfold axis is. So, my fourfold is out here. So, this implies that theta equals pi by 2. Therefore, the conductivity in a direction in the basal plane should be, so sine square pi by 2 is 1. So, this is sigma 1 1 and cos square theta is 0. So, therefore, in the basal plane the conductivity is independent of the direction. You can even say that it is, conductivity becomes isotropic in the x1 y1 plane. So, conductivity is isotropic in the x1 y1 plane. This is true for all tetragonal crystal systems. Now, let us expand this to the case of cubic crystals. In the case of cubic crystals, the conductivity tensor becomes, go back to the last lecture, sigma 1 1 0 0 0 sigma 1 1 0 0 0 sigma 1 1. So, conductivity vector, or rather the conductivity in the direction of the unit vector n is sigma 1 1 sine square theta plus sigma 3 3 cos square theta. I have just rewritten the same equation from here. In fact, I had this equation in another form. If I write it in that form, it is sigma 1 1 into, let me write it in this form, n 1 minus n 3 square plus sigma 3 3 n 3 square. Now, here sigma 1 1 equals sigma 3 3, because this is a cubic crystal. So, if this is a cubic crystal, then clearly sigma simply becomes sigma 1 1. And now, in this case, the direction is a general direction, the unit vector is in a general direction, not just in the basal plane like we did in the tetragonal crystal. And basically this statement is showing that conductivity is isotropic in all directions. So, if I measure conductivity by applying an electric field in any direction, I will measure a flux. The ratio of that would give me the same conductivity in any direction. Now, let us take, before I conclude this lecture, let us take some examples of second rank property tensors. Let us list down some examples. So, some examples of second rank property tensors. First example, let us take Fourier law of heat flow. This Fourier law of heat flow is given by this equation, where this is the temperature gradient. So, this is like the cause vector or the force vector, and this is the heat flux, and so therefore, this is the effect vector, and this is K is the thermal conductivity tensor, whose rank is 2. So, this is a second rank tensor. This is symmetric as well. So, it will follow, it will have the same properties as the general second rank tensors we have been dealing with. So, in the case of tetragonal, the basal plane heat flow will be isotropic. In a cubic crystal, heat flow will be isotropic in any direction. Now, second example is we can take a diffusion tensor. In this case, the flux is given by minus d del C, where this is the concentration gradient vector. This is flux, or you can even say chemical flux, because here some species is diffusing down the concentration gradient, and D is simply second rank tensor. The third example, magnetic susceptibility. Here you get magnetization equals chi, the second rank tensor for susceptibility, times the applied magnetic field. Magnetization, and this is the susceptibility tensor. Another example that I could take is a thermal expansion tensor. Here let's say there is a bar of length L, which is kept at a temperature T. Now, if the temperature is increased to T plus delta T, then the length of the bar goes from L to L plus delta L. So, there is a thermal expansion. In this, the change in length is proportional to the length at temperature T, and delta L is also proportional to delta T. So, we can define linear expansion coefficient alpha, which is 1 upon L delta L upon delta T. Now, it is not that expansion will take place only in one direction, expansion takes place in all directions. Hence, alpha would be a second rank tensor, and it would be symmetric as well. And we can write the, as a result of a temperature change, there is a strain that develops in the crystal, and that strain can be represented by epsilon, which itself is also a second rank tensor. So, epsilon ij equals alpha ij delta t. Now, in this case, delta t is not a vector, it is a scalar, or you can call it as a tensor of rank 0. So, alpha ij would have, this is tensor of rank 2, this will also be symmetric, and this will be symmetric because epsilon ij is also symmetric. So, epsilon ij is a strain tensor whose terms one can write it as epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 2 1, epsilon 2 2, epsilon 2 3, epsilon 3 1, epsilon 3 2, epsilon 3 3. So, this is strain tensor rank 2 and symmetric, and because this is symmetric, the thermal expansion tensor alpha is also symmetric, and therefore, even this tensor, thermal expansion tensor, will follow the same rules for all other second rank tensors that we have been discussing. Finally, one last example is the Seebeck effect. Now, what is the Seebeck effect? It actually is it occurs when conduction of heat and electricity occur together. Interference of these two processes, that is conduction of heat and conduction of electricity, result in what is called as thermoelectricity. So, here the electric field vector is related to a second rank tensor S into the temperature gradient. So, S is a second rank tensor. So, it is a difference in the temperature produces this electric field, and this happens when you have two dissimilar materials. See, if I have two dissimilar materials which are connected at one end, this is called as the hot junction. Out here is the cold junction, and these are two different materials which produces an EMF. You measure the EMF, and that EMF is related to, actually this is, that EMF is related to the difference in the temperatures of the hot and the cold junctions. And therefore, such a device is used for measuring wide range of temperatures, ranging from very low temperatures to very high temperatures, by appropriately choosing the two materials to make what is called, this device is what is called as a thermocouple, and this is a very commonly used device for measuring, for example, furnace temperatures, and this gives up quite an accurate measure of temperature. One thing to note about this is this second rank tensor, is, this is one example of a tensor which is not symmetric. So, this is a tensor which is not symmetric, and therefore, this will have 9 independent components. There is a reverse effect which is called as a Peltier effect, where you apply an EMF to get a temperature difference, and one of the applications of this is, these are Peltier coolers which can lower the temperature in a small chamber. With this, I conclude this lecture. Thank you.